Welcome to week 2 of MBA 602B. We're going to talk about probabilities and expected values, and then we're going to finish off the discussion with normal probability. Two of the most important concepts, I believe, in probability theory are these two concepts. You can add two probabilities to get the probability of their union if the two events are mutually exclusive. And what mutually exclusive means is their intersection probability is zero. The probability of their intersection is zero. An example could be a bunch of job applicants. Right? People are either hired or they're not. You can't be both, right? So being hired and not being hired are mutually exclusive, right? Another example might be in a classroom with black and white students. If there are no students in the classroom who are biracial, they're either white or they're black, then being black and white, those events are mutually exclusive. Nobody is in that intersection. In my household, though, my wife is black, I'm white. Our kids are black and white. And we have 4 of them. So the probability of being black and white in our household is 4 divided by 6. Now, interesting enough, the probability of being black or white in our house is 6 out of 6. Everybody in our household is black or white. So the union probability is more inclusive than the intersection probability. In our household, black and white club is 4 of 6. The black or white club is 6 out of 6. So in our household, being black and white are not mutually exclusive events. If they are mutually exclusive events, then you can just add their probabilities to get the union of probabilities, the probability of the union, right? Another concept is independence. If A and B are independent events, then you can multiply their probabilities to get the intersection probability. An example might be at a company that doesn't discriminate, race and hiring are probably independent. So if A is the event being hired, and B is the event of the applicant's race, then you can multiply the probability of being hired times the probability of a given race, and that will equal the probability of being hired and being of that particular race. Okay, so these are two of the most important concepts, I think, in probability theory. If events are independent, you can just multiply their probabilities. If events are mutually exclusive, you can just add their probabilities. So I want to start the class off with that. Okay, here are some examples using relative frequencies from U.S. Census data. So we have the percent of people who are between the ages of 0 and 19 in the U.S. being 29%. 7% of the nation is between 20 and 24. 14% of the nation is between 25 and 34. 16% of the nation is between 35 and 44. 13% is between 45 and 54. And 9% is between 55 and 64. And then 12% of the population, 65 or older. Okay, so that's U.S. Census data from more than 10 years ago. So things might have changed a little bit since then. Now we're going to let A be the probability event, let A be the event 55 years of age or older. And we want to compute the probability of not being an A. So the probability of being an A is 0.21. We just add these two, right? Notice we can just add these two. Why can we add these two? Because this event and this event are mutually exclusive, right? Nobody can be between the ages of 55 and 64 and at the same time be older than 65, right? Nobody can be in that group. So these two events are mutually exclusive, this event and this event. So we can just add their probabilities together and we get 0.2100, right? 0.12 plus 0.09. The probability of not being an A can be found by adding up the probabilities of these mutually exclusive events, right? Adding these up, and we get 0.7900. Or we can use the complement rule. The complement rule is 1 minus the probability of A, and we get the same answer. All right, so let A be the event 55 years of age or older. Let B be the event 64 years of age or younger. We want to compute the probability of A and B. So the probability of A, again, is 0.210. These two events are mutually exclusive because there's nobody that can be both in this age group and at the same time in this age group. The event B is 64 years of age or younger, right? And this event, 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 all those events are mutually exclusive. So we can just simply add up these probabilities, right? Because they're all mutually exclusive. There's nobody, you have to be in one of the age groups. You can't be in two. So each of these events are mutually exclusive. And we can add these probabilities up and we get 0.88. Now we want to compute the probability of A and B. So A is that event, B is that event, and you can see that there's an overlap, right? You can see there's an overlap. And the overlapping event is 55 to 64, right? The overlapping event is 55 to 64. So the probability of A intersect B is this area right here, the overlap, the intersection, if you will. The intersection of the red box and the blue box makes a purple box. So the probability of that intersection is 0.0900. What about the probability of A and C, where A is the probability of 55 years of age or older, and C is the probability of 24 years of age or younger? Well, these two boxes don't intersect, right? You can't be younger than 24 and older than 55 at the same time. So this probability is 0. So this event and this event are mutually exclusive, which makes perfect sense because you can't be, again, less than 24 at the same time you're older than 55. Okay, now we're going to calculate the probability of A or B, right? A or B. Now A, again, is 55 or older, right? And its probability is 0.2100. B's probability is 0.88, and it includes people who are 64 or younger. And remember, there's an intersection, right? So A and B are not mutually exclusive. They have something in common. The people who are between the ages of 55 and 64, right? So here we have to subtract off that intersection probability. So when events are not mutually exclusive, their intersection is not 0. We can't just add their probabilities, right? If we added their probabilities, we'd get an overcount, right? We'd overcount because we're double counting this group here. So we have to subtract off the intersection, and we get 1, right? Okay, now let's compute the probability of A or C, right? Event A was 55 and older. Event B was 24 or younger, right? So the probability of C is 0.36. We just add those two together. The probability of A was 0.21. So for the union of A and C, we can just add the probabilities because there's nothing in common between these two events, right? A and C are mutually exclusive, so this is 0, right? So this goes back to that rule. If A and C are mutually exclusive, we can just add their probabilities to get the union. And we get 0.57. Okay, conditional probabilities. We use conditional probabilities to determine independence. of events. And if you're a firm who wants to avoid a lawsuit over discrimination in terms of hiring or its promotion practices, you need to be aware of this rule. I mean, if you're just interested in being a good company in society today, you want to avoid discrimination, right? It's not just because you want to avoid the lawsuit. It's just that the company is headed by people who care about treating people fairly, right? So you want to avoid discrimination. And you can use the conditional probability to figure that out. The conditional probability of A given B, this line here means given, the word given. This means and, right? So this is the intersection probability. So if A given B, right, that right there, that probability equals the probability of A and B divided by the probability of B, right? So if I have the probability of A given B, I know that I have to divide by the probability of B, right? I have to divide the probability of A and B by the probability of B, right? So I have the probability of A and B divided by the probability of B. And the best way to think about this is in a crosstab. Here we have white and black applicants to a job. 160 people were hired. There were 820 people not hired. There are a total of 900 applicants. 280 of those applicants are black, and 7 of those applicants are white. So the probability of hired is 160. There are a total of 160 people hired, and 980 were had applied. So that ratio is 0.1633. Now, this is another way you can calculate a conditional probability. We can, here we're saying we want the probability of hired given the applicant was white. So what we're doing basically is we're looking at only the white applicants. And 130 of the white applicants, and there are 700 applicants that are white, 130 of the white applicants were hired out of a pool of 700 white applicants. So when you take 130 divided by 700, you get 0.1857. That's another way to calculate conditional probability, right? And then that probability is different from the probability of being hired. So when these two probabilities are different, we say that events H and W, being hired and race, are dependent events. And you can go a step further. Since this probability here, since this probability of being hired is larger than this probability of being hired, this probability of being hired, given you're white or black, this probability of being hired, given that you're a white applicant, since this probability of being hired is greater than this probability of being hired, you might say there's a disparity or even a discriminatory process going on here, right? If this firm is purposely not hiring black workers because they're black and wanting to hire white workers because they're white, then you could say they're discriminating, right? And the firm is setting itself up for a lawsuit and really bad publicity, right? So when these two things are different, you can say that they're dependent events. Now, in more advanced statistics, when we get into hypothesis testing, we can use a chi-square test to determine if these relative frequencies are statistically different. We can use a chi-square test to do that using frequencies, or we can use a two-proportion test to determine if these are different in a statistical sense. It may be the case that these two differences, that difference is insignificant, right? So if this difference is insignificant, we'd conclude that events H and W, being hired and race, are probably not dependent events, right? But if this difference is statistically significant, we might conclude that being hired and race are dependent events, right? We haven't got that far yet, so all we're looking at right now is a difference, right? And the interesting thing about it is, in real world data, there's going to be a difference. There's going to be a difference. It's just if that difference is significant or not. Okay, here's another example. Here we're considering the promotion status of economists, where economists are classified as either female or male, right? The probability of promotion, there's 120 people promoted, and there's a total of 720 people at this economics firm, right? So the probability of being promoted is 120 divided by 720, right? This is the probability of being promoted given the employee is male, given the economist is male. And if we're looking at just males, 500 were not promoted and 100 were promoted. And 100 divided by 600 is the probability of being promoted given that you're male. Okay, and we can see that this number is identical to this number. And when the two numbers are identical, we can say the two events, promotion and gender, are independent events. So identical, the conditional probability being identical to the marginal probability, the probability of being promoted. When these two things are identical, we can say the two events are independent events. Okay, now we're going to look at Bayes' theorem. This is an interesting example. The example I bring up is interesting with respect to a thing that we call prevalence, right? If a community has a very low history or very little drug use, and then a teacher is on the news arrested for selling illegal drugs out of their house, the school board might want to get in front of it by doing a drug test on all of its school teachers and staff. Now, if drug use is not really extremely low in the community, that's probably a wise decision to do. But if the drug testing is an overreaction because the community, there hasn't been an issue of drug use in the community forever, then an interesting thing happens. People who test positive in the drug test, a large percentage of them could be incorrectly fired. And so this example is an extreme example where prevalence is really low, right? And when it's really low, decision makers got to be really careful. They need to understand this Bayes theorem. When this percentage isn't really low, then whatever testing they're doing, whether it's drug testing or disease, virus testing, probably not an issue. But when the incidence of an event is really low, when an event is really rare in a population, you got to be really careful with testing. So in this example, we're going to assume there are 10,000 employees and 1% of them are druggies, right? So we have a company that is pretty clean. 99% of 10,000 employees are clean and 1% of them are druggies. Now, if an employee is found to be a druggie, the company is going to fire them for safety reasons. And so we're going to contract with a laboratory that claims that their drug test is 94% accurate, but that test has a 5% chance of producing a false positive. Okay, those numbers are pretty reasonable across different kinds of tests. I think you'll find those kinds of accuracy rates and false positive rates in many laboratory tests. So P is the event test is positive, N is the event test is negative, D is the event employee is a druggie, and C is the event employee is clean. Now, this is our prevalence rate, right? 1% of the population is using drugs in the company. So one out of every 100 people in our company of 10,000 are using drugs. So it's kind of small. Okay, so from the drug lab, we know that the probability of somebody testing positive given they're a druggie is 0.94. That's the accuracy of the test. From that same test, we know the probability of testing positive given the person is clean is 0.05. This is the false positive rate. So this is reported by the drug company or the lab with its test, and this is reported by the lab, right? This is part of the company's brochure, right? We have a 94% accuracy rate, and we have a 5% false positive rate. And this is the information we know from the community or the company. We don't have a lot of drug users in our company. Only 1 out of 100 are, right? Now we need the probability of being clean in the company. And that probability of being clean is just a complement. 1 minus 0.01, which is 99.99, right? So 99% of our employees are clean. Down here, the probability of somebody testing negative given they're a druggie is the complement of this, right? So 1 minus 0.94. So if you're a druggie, the probability that you test positive is 0.94, accuracy of the test. If you test negative and you're a druggie, that's got a 6% chance of occurring. Now down here, we have the probability of positive given you're clean. This is the false positive rate, which is 5%. This is the complement of that event, right? This is the complement. So 1 minus 0.05 is 0.95. This is the probability that you're negative given you're clean, right? And those numbers make us feel good, right? They make us feel good. Okay, so these are the probabilities that are going to feed the thing that we want to know. What we want to know is what's the probability of a person being a druggie given they tested positive. That's what we really want to know, right? In this situation, we're going to find out that we're firing a lot of people who are clean, who happen to test positive for drug use. Okay, so we're going to build a decision tree. So we give people, people are split into 2 groups. We have the druggies, which is 1 in 100 of our 10,000 employees. And then 99 out of 100 of our employees are clean. And we again have 10,000 employees. Okay, now we're going to give them a drug test. We're going to give, if we know who the druggies are, we give them a drug test, right? If we give the druggies a drug test, right? So on this branch, we've been able to, we know which ones are druggies. And on this branch, we know which ones are clean. So on this branch, given they're a druggie, right? Given they're a druggie, what's the probability they test positive? Well, that was 0.94. That's our accuracy rate, right? Given that they're a druggie, what's the probability they test negative? 0.06. 1 minus that, right? And then down here, this is the clean branch, right? So given the probability, given that the employee is clean, what's the probability of testing positive? 0.05. That is our false positive rate. And this is the complement, right? 1 minus 0.05. So this is the probability of testing negative given you're clean. And this is what we hope the clean employees, what happens to the clean employees, they test negative, right? Okay, so our experimental outcomes here are what? If we go back to our conditional probability rule, we can rewrite our conditional probability rule as the probability of testing positive and being a druggie. That would be equal to the probability of positive given druggie times the probability of druggie, right? So we're just going to multiply these two probabilities. So this right here is just a rearranging of our conditional probability equation. So all we're doing here is we want to calculate this probability, and we're multiplying both sides by the probability of B, right? So when we multiply this side by probability of B, the probability of B is canceled. And now we got the probability of A and B equaling the probability of A given B times the probability of B, right? So we're just rearranging this equation to complete our decision tree. So we want to know the probability of testing positive and being druggy. You just multiply these two probabilities, right? We want to know the probability of testing positive and being clean. That's just multiplying these two probabilities. And this is the when you add these two together, this is the probability of positives, right? When you add these two together, that's the probability of positives. So to get the probability of negative and druggy, you take the probability of negative given druggy times the probability of druggy, and you get 0.0006. You go to the probability of negative and clean, you multiply the probability of negative given clean times the probability of clean. 0.99 times 0.95 is 0.9405. And when we add those two together, we get the probability of negative. Just something I'm noting, right? So these are our experimental outcomes, right? We can have positive and negative, positive and druggy, negative and druggy, positive and clean, and negative and clean, right? Okay, so here's Bayes' rule, right? This is the thing I want to know, the probability of a person being a druggie given they tested positive. So when the company gets the results back, they get a list of all the company employees that tested positive. And the assumption is that if you tested positive, you're a druggie, so therefore the company needs to terminate your employment, right, for safety purposes, right? So this is the thing that we really want to know, right? We want to know what this is. This is the probability of being a druggie. So this is the prevalence rate, right? This is the prevalence of drug use in our company, and it's 1%. This is the accuracy rate of the drug lab's drug test, right? This is the drug lab's false positive rate right here. And this is the portion of our employees that are clean. So the complement of being a druggie, right? So this is 0.01, this is 0.99. So now we just fill in our information, right? We've already calculated this, right? This right here is just the probability of being a druggie and being positive. That's what this is. Being a druggie and positive. We calculated that in the tree, right? Being positive and a druggie. You take this product here, right? So we've already calculated that. Now this right here is the same thing, right? Is that right? The probability of druggie and positive. This is the probability of, this product here is the probability of being clean and testing positive. So we go back to our tree, the probability of testing positive and clean. So when we add these two up, we're calculating the probability of positive, aren't we? You see that? When we add these two together, we're calculating the probability of positive. So this down here is the probability of positive, right? This down here ends up being the probability of positive. When we add the probability of druggie and positive to the probability of clean and positive, this whole thing down here is the probability of positive, right? Which makes sense because we want to know the probability of being a druggie given that you're positive, right? So when we do the arithmetic, which we've already done in the tree, we get 0.1596. What does that mean? Okay, so if you get a list of people who tested positive, right? You're the company, about 16% of the people who the drug lab says tested positive, only 16% or 15.96% of the employees in your company who tested positive, only 16% of them are actually drug use. That's kind of interesting, right? So that means if you fire every employee that tests positive, you're firing 84% of the people you're firing are actually clean. So when the prevalence rate is really, really tiny, when the prevalence rate is really, really small, a decision like drug testing your entire group of employees will result in 84% of the people being fired for testing positive being false terminations, which could set you up for a lawsuit. Okay. Now we're going to look at a couple of discrete probability distributions. The first is a uniform discrete probability distribution, and it's a pick one lottery. And this pick one lottery, there are 10 ping pong balls in a bucket. Each is labeled 1 or 0 to 9. So this is the first ball, the second ball, the third ball, the fourth ball, and the 10th ball, right? So there's 10 balls in a bucket, and you pull out a ball. The probabilities of each of these outcomes, they're all equal, right? Each has equal probability. So this right here says the probability of getting a 0, the probability of drawing a 0 from the bucket is 1 in 10. The probability of pulling a 1 out of the bucket is 1 in 10. The probability of pulling a 2 out of the bucket is 1 in 10. Yada, yada, yada. The probability of pulling a 9 out of the bucket is 1 in 10. When you add these probabilities up, you get 1. Relative frequencies add up to 1. You can think of these as relative frequencies. You can think of those probabilities, right? A probability distribution sums to 1. Now, the expected value of this distribution, down here, the expected value of this distribution, there's 10 balls. And because we start at 0 instead of 1, we take 10 minus 1, right? If this started at 1, we wouldn't do it this way, right? But this starts at 0, so there's 10 ping pong balls in this bucket. 10 minus 1 is 9. 9 divided by 2 is 4.5, and that makes sense, right? We got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, right? So we're going to fall in between, right? So our expected value is 4.5. Remember, this is 0 here, right? This is 0. So another way to think about this is when we multiply 0 times 1 over 10, 1 times 1 over 10, 2 times 1 over 10, yada, 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 9 times 1 over 10. When we add that up, and when we add those products up, we're going to get 4.5. So 0 times that is 0, right? So 1 times this is 1 divided by 10. This is 2 divided by 10, 3 divided by 10, 4 divided by 10, 5 divided by 10, 6 divided by 10, 7 divided by 10, 8 divided by 10, 9 divided by 10, right? If we factor out dividing by 10, we get the sum of these numbers divided by 10, and that's 4.5. So that hopefully that makes sense, right? And then our variance is the 10 squared, so 100 minus 1, so this is 99 divided by 12, which is 8.25. And then our standard deviation would be the square root of that. So that right there is a uniform distribution. Uniform distribution. Okay, so now let's look at a binomial distribution. We have a pick 3 lottery, right? So we're going to use the binomial distribution to calculate a pick 3 lottery winning and losing, right? So this pick 3 lottery, we're going to do a straight. We're going to check mark straight on the pick 3 lottery card. Okay. And that means we not only have to pick the winning numbers, but we have to pick the order in which they're pulled out of the bucket. So the first bucket, let's say and we're going to bet $1. So in the first bucket, we pick a 5, right? We pick a 5. So the 5 has to come out of the first bucket. So the first number is a 5. Out of the second bucket, we're going to say a 1 is going to come out, right? And out of the third bucket, we're going to say a 2 is pulled out, right? So if we get any other number in the first bucket, we lose. If we get any other number in the second bucket, we lose. If we get any other number but 2 in the second bucket, we lose. We have to get a 5 in the first bucket, a 1 in the second bucket, and a 2 in the third bucket, right? That's what we have to pull out. So we're going to win $500 if the winning numbers in this order are 5, 1, and 2, right? A straight, again, is 3 digits in the exact order. Any 3 digits, right? We could have done 1, 1, 1. It doesn't change our chance of winning, right? Our chance of winning is 1 in 1,000 because if we pick the winning number in this bucket, and the winning number in this bucket, and the winning number in this bucket, we know that probability is 1 in 10. This one's 1 in 10. This one's 1 in 10. We can simply multiply 1 divided by 10 times 1 divided by 10 times 1 divided by 10, because pulling a number out of here has no effect on pulling a number out of this bucket. And these two numbers that we pull out of the first 2 buckets, that has no bearing on what number we pull out of the third bucket. Because when we pull the first number out, there's 10 numbers in there. When we pull this number out of a different bucket, there's 10 numbers in there. When we pull this number out of the third bucket, there's 10 numbers in there. Okay? Okay, so let's do a tree diagram first. In order to win the lottery, we have to get the first bucket correct. So this means we pick the first number correctly from the first bucket. And this has a probability of 1 in 10. This has a probability of 9 in 10. There's 1 5 in a bucket of 10 numbers. There are 9 numbers in a bucket of 10 that aren't the winning number, 5, right? In the second bucket, if we were able to successfully pick that first number, right? So given that we picked the first number correctly, we now can either pick that second number correctly or we can incorrectly pick it, right? Again, there's 1 choice in that second bucket that works. There are 9 that don't work. Okay. So if we had failed to pick the winning bucket, a number in the first bucket, we have a 9 in 10 chance of doing that, right? Given that we failed, right, in the first bucket, we can either pick the winning number in the second bucket, or we can pick the losing number in the second bucket. And this is much harder to do than this, because there's 1 in 10 of those, and there's 9 in 10 of those, right? So now, given that we were successful in the first bucket and the second bucket, what can happen? In the third bucket, we could pick the winning number of the third bucket, but we could also pick the losing number of the third bucket. Same goes for this situation, and that situation. Okay. So on this top branch here, we have win and win and win. So we want to know the probability of win and win and win, right? On this branch, we want to know the probability of win and loss, right? Oh, Down here, we want to know the probability of loss and loss and loss. So probability of loss and loss and loss, right? Okay, these branches, what these branches have in common is there's one loss, right? There's one loss on this branch and two W's. On this branch, there's one loss and two W's. And on this branch, there's two W's and a loss, right? So this is the probability of win and loss. This is probability of win and loss and win. Then down here we have the probability of loss and win, right? And there's three of those, right? There's three where we have two losses. Win and loss, win and loss. Then there's loss and win and loss. So loss and wind and loss. And then we have loss and wind. Win. So probability of loss and win, right? Now, because the buckets, pulling a ball out of one bucket is independent of pulling a ball out of a second bucket and pulling a ball out of a third bucket. Since those are independent events, pulling numbers out of buckets, right? Each having balls numbered 0 to 9 in them, that process involves independent events. So we can rewrite each one of these as the product of probabilities. See that? We write that. So that equals the probability of W times the probability of W times the probability of W. And what this means is the probability of win when these are independent events. Independent events. Sorry. And we can do the same thing for the ones where we have one loss, right? Here we have the probability of win and loss. So the probability of win times the probability of win times the probability of loss. And we have the same thing down here, except we have the probability of win times the probability of loss times the probability of win. And then down here we have the probability of loss times the probability of win times the probability of win. And then we have two losses, and two losses. So that's why we have probability of loss times probability of loss times probability of win. Probability of loss times probability of win times probability of loss. And then we have the probability of loss times probability of loss times probability of win. And then down here we have the probability of loss times probability of loss times probability of loss. Okay. Now I'm going to replace PW with 0.1, right? PW with 0.1. See that? I'm replacing PW with 0.1. Because when we pick the winning number for a bucket, that probability is 1 in 10, or 0.1, right? The probability of loss is 9 out of 10, right? 9 out of 10, or 0.9. So everywhere we see a probability of loss, we can write 0.9, right? 0.9. And we just do the arithmetic. So this times this times this is 0.001. This means there's x equal 3 means there's 3 winners. 1, 2, 3, right? So x equal 3 is the number of wins. Here, in this situation, we have 2 winning numbers, right? So x is the number of winning numbers. We have 2 here, we have 2 here, and we have 2 here. In this in these branches, we have 0.9 times 0.9, which is 0.81, times 0.1, which is 0.081. So in these 3 branches, we have 2 losses and 1 win. So that's why x equals 1 here, right? And then down here we have 0 wins, right? 0 wins. Okay. Now these are all in red because I win nothing in the straight lottery. I win nothing. I have to pay $1 for the right to win $500, but These are all red because I don't win. I don't win. I can only win one way, right? I can only win one way. I picked the winning number in bucket 1, bucket 2, and bucket 3. Okay, so this is the probability that I get all 3 balls correct. When I add the 0.09 to the 0.009 to the 0.009, there are three ways to get 2 winning numbers, right? Win, win, loss. Or sorry, there's 3 ways to get 2 winning numbers: win, win, loss, win, loss, win, and loss, win, win. So I have to add this probability to that probability to that probability, right, to get the 0.027. Now, to get the probability of getting 1 ball correct, there are 3 ways to do that: win, loss, loss, win, loss, win, and win, loss, loss, win, loss, loss. Wait a minute. Win, loss, loss. Loss, win, loss. Loss, loss, win. So there's 3 ways to get 1 number picked correctly. We add these 3 up and we get the probability of getting 1 ball correct. And then we have the probability of getting 0 balls correct. There's only one way to do that, right? So x equals 0 because we didn't get any of the winning numbers correct, right? So you can use the binomial distribution function in Excel to calculate this probability here by typing 3. 3 is the number of correct balls picked. This 3 is the number of trials. This is the probability of success in this binomial experiment. And this means don't accumulate the probabilities. We want the probability distribution function, not the cumulative distribution function. So we put false there. So when you type that into an Excel worksheet cell and you hit enter, you'll get this value. If you type equal binomial dist parentheses 2 for 2 winning numbers out of 3 with a probability of success of being 0.1 or 10%, and that argument being false, we'll get 0.009. If we change the 2 to a 1, where we only get 1 of the 3 balls correct with a probability of 0.1, then when we hit enter on this command, we'll get 0.243. And then down here, if we plug in 0 instead, we get 0 out of the 3 balls correct with a 0.1 probability for getting the ball correct. We get 0.729. So the probability of winning here is this, right? The probability of winning is this. The probability of losing is the sum of these 3. So 0.99. And this makes sense because this plus that is 1, right? So what we're doing is we're converting this binomial distribution into a distribution where there's only 2 outcomes. I win or I lose. The probability of I win, the probability that I lose, right? Now, with these probabilities, if I win, what do I win? I win $500 minus the dollar I used to play the game. And that is a probability of 0.001. The probability I lose, well, I win nothing, but I had to pay $1, right? I had to pay $1. So this is what I win on net, right? This is what I win on net if these are my net winnings if I get all 3 balls correct. These are my net winnings if I don't get all 3 balls correct, right, with a probability of 0.99. So what are your expected winnings? Well, I take this outcome here, $499, and I multiply by its probability. I take this outcome here, a negative $1 times that probability. And so the expected winnings of a pick 3 straight with a straight option chosen You're going to lose 5 cents on every dollar bet. Now, if you go to Vegas, the government mandates that the house, the casino, the privatized casino, I think most of them are, the house can only win 5 cents on every dollar bet. What does that tell you? Don't gamble, right? The house wins. The house wins because they're setting up the game in a way that, on average, over the long run, they're going to win 5 cents on every dollar bet. It's even worse if you play state lotteries. The state doesn't like the competition from Vegas, so it mandates that Vegas gambling houses win only 5 cents on every dollar bet. Meanwhile, the state in its gambling rackets in this pick 3 game are winning 50 cents on every dollar bet. So when you gamble with the state, playing the state lottery, you're voluntarily paying higher taxes, right? If you're going to gamble, the best thing to do is to go to Vegas, right? Where the state tells the house that they can only keep 5 cents of every dollar bet, right? So the state being a player in the gambling market, at the same time the state is the umpire, skews the game toward it, right? It's going to take 50 cents in this particular game out of every dollar you bet, where it's maxing the expected winnings of the house, 5 cents on every dollar bet. Okay? So you're better off, if you want to gamble, the best thing to do is not gamble, because you're going to lose in the long run. The average person is going to lose in the long run. So the best decision is not to gamble. But if you want to gamble, the best place to do it is in Vegas. Okay? Now let's go to the Powerball. The Powerball is different, because the Powerball, you pick, in this particular Powerball, you pick 5 numbers from one bucket that has numbers from 1 to 59. So in this particular Powerball, one bucket has 59 balls in it. The Powerball bucket has 39 numbers in it. So you get to pick one number from the Powerball bucket, and you get to pick 5 numbers from the bigger bucket, right? So when that first number is pulled out, when you pick that first ball, when that first ball is chosen, there's 59 balls in the bucket. After that first ball comes out, there's only 58 balls in the bucket. After that second ball is chosen, there's only 57 balls in the bucket. After that third ball is chosen, there's only 56 balls in the bucket, right? So you can see that these first 5 balls, these choices are no longer independent. Their values depend on what happened before, right? For example, and you can't, obviously, you can't pick 1, 1, 1, 1, 1, right? You can't do that, right? So you can't pick duplicate numbers here. But your Powerball can be one of these, right? The Powerball can be one of these. So you could pick 1, 4, 2, 8, 30, 53, right? From this bucket. Your Powerball can be 37, or your Powerball could be 1, or your Powerball could be 4, or your Powerball could be 28, your Powerball could be 30, your Powerball could be 53, right? It could be any of these numbers. Well, it can't be 53 because it only goes up to 39. So it can be 1, 4, 28, 30. It can't be 53. Or the Powerball can be 37, right? So the Powerball could be one of these numbers, not the 53. There's no balls over 39, right? So you could have a duplicate Powerball number. I don't think I've ever seen that, though. but I don't watch the Powerball all that much. So what we have to do here in this particular problem is we have to calculate the probability of the first 5 numbers, right? And we have to calculate the probability of the Powerball. The probability of the Powerball is real easy, right? If you get the Powerball, the probability of you getting the Powerball correct is just 1 divided by 39, right? You pick one ball out of a group of 39. So that probability is easy, right? And since this bucket of balls is a different bucket of balls than this one, these two events are independent, so we can just multiply these two probabilities once I know the probability of the first 5 numbers. Now, to calculate the probability of the first 5 numbers, you need a hypergeometric distribution function, right? So in the first 5 numbers, there are 59 ping pong balls numbered 1 to 59. You're going to choose 5 of them, right? You need 5 of those 59 numbers to win. Okay. Your sample size is 5. You select 5 ping pong balls, right? And in this, we're gonna pretend the Powerball is a very, very simple lottery, right? There's only one way to win, and that's to get all 5 of these numbers correct. Now that's not the case. We're just gonna keep it simple, right? We're just, I think most people that play the Powerball want the Powerball jackpot, and the other ones are just not that important, right? So we're going to assume that this Powerball lottery only pays out if you get these 5 numbers, right? Correct. So we're going to use the hypergeometric distribution. In Excel, you'd type equal. In a cell, you would type equal. You don't type anything in front of the equal. You type equal hyper or hype, HYP, geom, hype geom, hypergeometric, hype geom dot dist, and then 5, 5, 5, 59, and then false. When you do that, you get this number here, 0.0000001997, right? So this is the probability of the first 5 numbers, right? The probability of the first 5 numbers. So to get the first 5 numbers and the Powerball, right, you take this probability times the Powerball probability. And so we just substitute this into here. We substitute this value into here. And we get a probability of 0.0000000512, right? So in this particular Powerball, we're assuming you only win one way. You have to have all 5 and the Powerball, right? So this is the probability of winning, right? In this simplified version of the Powerball. This is the probability of winning. And if it's a $20 million jackpot, you had to pay $1, right, for the right to win the $20 million jackpot. 20 million minus 1 is 19,999,999. And that probability is 0.0000000512. Now, in this simplified version of the Powerball, we're going to lose otherwise, right? And when we lose, our net winnings are negative $1 because we had to pay $1 to play, and then we win nothing if we get any other set of balls. Okay. And so this probability is just 1 minus this, right? 1 minus this is that probability of loss, right? And so to calculate the expected winnings, we multiply this by its probability, and we multiply this by its probability, right? So we're multiplying this by the probability and this by the probability, and we get an expected loss of 90 cents of every dollar we bet. Okay, so again, the moral of the story is don't gamble because you're going to lose. The house wins over the long run. That doesn't mean individuals don't win. It's just the average person, when they gamble, they're going to lose, right? They're going to lose. If you have to gamble, the best choice is to go to a place like Vegas, right? Where the state says they this is capped at minus 5 cents on every dollar bet, right? Okay, so that's the hypergeometric distribution. Now we're going to look at the normal distribution. The normal distribution is a bell-shaped curve, right? It's symmetric, and there are infinite many of these bell-shaped curves. The one shown here has an expected value of 4. So because it has an expected value of 4, the center of the distribution is at 4. The shape of the distribution can take on infinite many values from 0, from a number really close to 0 to infinity, right? So the shape of this distribution could have the shape can be determined by a standard deviation of 0.000001 to a billion, a trillion, right? So there are infinite many shapes of this normal distribution, right? The mean determines where the center is located, and the standard deviation determines how tall it is. The taller it is, the skinnier it is. The shorter it is, the wider it is, right? And the wider it is, that means a wide normal distribution has a big standard deviation. A tall and skinny normal distribution has a small standard deviation. So this is the normal distribution for a mean of 4 and a standard deviation of 2. If the mean changes from 4 to 8, the shape of the distribution doesn't change. It's just its location shifts, right? It's not any wider, it's not any taller. It still has a standard deviation of 2, right? The mean changes, it just shifts it up the center of the distribution to 8. And if the mean changes again, it just shifts the distribution down to 6, the center of the distribution down to 6. The shape has not changed, has it? See? The shape has not changed. The shape has not changed because the standard deviation is constant at 2. Okay. What happens if the standard deviation changes? If the standard deviation goes from 2 to 4, what happened to the distribution? It's still centered at 6, it's just shorter and wider, right? And then here the standard deviation is 3. So a standard deviation of 3 is going to be in between, in terms of height, it's going to be in between a normal distribution of a standard deviation of 2 and one with the standard deviation of 4. It's going to be in between, right? Okay. And the one in between is going to be not as wide as the one with the bigger standard deviation. It's going to be wider than the one with the smaller standard deviation, right? Okay. Now, because a textbook can only be so wide, there's only one normal distribution in most textbooks, and that's the standard normal. And the standard normal has a mean of 0 and a standard deviation of 1, right? And you can click on this link right here to view the standard normal distribution. I'll show it to you. So here's a standard normal distribution website. The mean 0 and the standard deviation of 1. If I change the mean to 4, notice what happened to the center of the distribution, right? This goes from 0 to what? 4, right? The shape of the distribution did not change. If I change the standard deviation to 2, what happened here is this z-value went from the z-value went from 5.96 to 7.92. In other words, it got wider and shorter, right? You can't tell, right? You can't really tell. Okay. So most of the time we're going to deal with a mean of 0 and a standard deviation of 1. Okay. Okay, so let's calculate areas under the curve. Areas under the curve represents probabilities. I want to know what the area under the, I want to know what the probability of z being less than -1. Graphically, That's this area that has infinite length, right? Or infinite width. This goes off into infinity. It gets closer and closer and closer to the horizontal axis. So instead of dropping out to infinity, we kind of just stop it. So you can imagine there's a yada, yada, yada here, right? This just continues to negative infinity. So what we're doing is we want to find this area, right? So we can find it in Excel by typing equal norm.s.dist. So we can type equal norm.s.dist and -1. And then true. True allows us to get the area, right? Because true means it's cumulative, right? From negative infinity up to -1. That's what that says. And we hit enter. And we get 0.15865. Now I like to report my probability values in 4 decimals. Okay, so we get 0.1587. Right? 0.1587, right? So I'm going to put 0.1587 in this red area because this red area represents the probability of the event z is less than -1. In our stat calculator right here, I'm going to put -1 here. Z value is -1. And I'm going to change it to left tail. See that? Change it to left tail. So this area here is 0.159. So this website uses 3 decimal places. And we can do the same thing in Excel. We can reduce this 3 decimal places, right? So 0.159. I like to use 4 decimals for probabilities. Okay. So that's in the statdistribution.com website. Now, what's the probability? What's this red area? That red area is the probability that z is greater than 1, right? So if we go over here, all we have to do is click right tail. See that? And then we have to change this to +1. Okay. And we get the same probability value. Why? Because it's symmetric, right? It's symmetric. In Excel, what we would do to calculate this probability here of z greater than 1, we would just use the principle of symmetry, right? You see that? We use the principle of symmetry. Okay, so this area would be 0.1587. Okay. Now the question is, what's the probability of z being between -1 and 1? That's this gray area, right? That's this gray area. So the way we get that is we take this, add it to itself, and we subtract this sum from 1, right? So we can copy this and pull it down. So this is the probability of z being less than -1. This is the probability of z being greater than 1, right? And then we just add them up. And we subtract that sum from 1, right? We subtract that sum, B4 plus B3, we subtract that sum from 1. And we get 68.2. I got 6 there. Yeah. I got a bit of round off error there. It should be, I think I used the value from a table to calculate that. Oh, no. What I did is I had a round off error, right? So what I did is I did this. We had a round off error. You see that? So I added the rounded value to a rounded value and I subtracted that from 1. That's why we're off. Okay. The actual more correct answer would be 68.27%, right? That'd be the more correct answer. Let's see what happens over here. All I have to do is change it to two tails. See that? I just changed it to two tails. So I got the -1 and the 1, right? And I subtract this from 1. I subtract this from 1. So if I go over here to Excel, I can find this white probability. I can find this probability by doing equal 1 minus 0.317. And I get 0.683. Which in either case would be correct, right? If I went to 3 decimal places. Okay. So that's how I'd find the probability of being in between -1 and 1. And if you remember from the empirical rule, that's what the empirical rule says, right? If the distribution is normal, you expect 68.26% of values to be within 1 standard deviation. Remember the standard normal distribution, the standard deviation is 1. So this is 1 standard deviation below the mean of 0, and this is 1 standard deviation above the mean of 0. So the empirical rule says if it's a normally distributed random variable, about 68% of the values will be within 1 standard deviation of the mean. Okay, what about within 2 standard deviations of the mean? The first thing we have to calculate is the probability of z being less than -2. So we want this area, right? And again, we use the same norm.s.dist function, right? Except we change the -1 to -2, right? We change this to -2. We change this to 2, right? So to 4 decimal places, we get 0.022, and then this would be an 8 because that's a 5, right? So we get 0.0228. And then we have to calculate the probability of being greater than 2. So the probability of being greater than 2 is 0.0228 by symmetry, right? And then the probability of being in between is 1 minus that and minus that, which is 0.9544, which is what we got here, right? Again, there's a discrepancy because I'm using the rounded off values. I'm using the rounded off values here, right? The actual answer is 0.9545. 0.9545, right? If you use the this website, you change the z value to 2, and the p-value here is the blue area plus the blue area, so 0.046. So 0.954. Okay, so 0.954. To three decimals, this would be 95.4% of values of a random normal variable. A normal random variable are within 2 standard deviations of its mean. Okay, and again, that's the empirical rule, right? And if we want to do within 3 standard deviations of the mean, we change it to -3, right? And we get that value. So if I go here, I'm going to change it to -3. So I want to find the tail probability. So I change this to -3, right? And I get 99.74, right? I get 99.74, the area within 3 standard deviations of the mean, right? Over here in the website, I change this z value to 3, and I can take this 0.003, change this to 0.003, and I get 99.7, right? 99.7%. Right, so there are several ways to get these calculations. Okay, so this question is different. Here, I give you the probability, right? I tell you the area under the curve in the lower tail is 0.0250. So I'm giving you the probability. And this number here has to be negative, right? Because this is a lower tail probability. You want the probability of z is less than some number, right? So when z is less than some number and that probability is tiny, that means you're on the left side of the distribution. So this has to be a negative number. To get this, you type equal norm dot s dot inv, right? So on this one, you type equal norm dot s dot inv. You use this function in Excel when I give you the probability, right? And the probability is 0.025. So the number is to 3 decimals, it's negative 1.96, right? Negative 1.96. Now over here, to get this number, I'm going to change the p-value to 0.025, and I'm going to change it to a left tail. See that? So the p-value is 0.025. It's a left tail, a negative 1.96, right? So that's how you can do that in this stat distribution calculator. Okay. So that question mark here is negative 1.96, right? If I do this, if I go up here and I change this to negative 1.96, what do you think I'm going to get? Whoops. I go back into this cell here and I type in negative 1.96. I get a probability of 0.0250, right? I just verified this, right? Just verified it. Okay. What is the value of minus z and z? So this one's different. What's the value of minus z and z, right? If the probability of being between them is 0.950. So if the probability of being between negative 1.96 and 1.96 is 0.950, what's this area here? Well, you have to take this and subtract it from 1, right? You have to subtract this from 1, and you got to divide it by 2 because you're splitting it up in 2 spots, right? So 0.250 plus 0.250 is 0.05, and 0.05 plus 0.95 is 1. So in this particular case, what you do is when I give you the probability of being between two numbers, right? This could be -2. If this is -2, that's 2. If this is -1, that's 1. So the absolute value of this is equal to that number, right? So these are the same numbers, except this one is negative, right? So we have to use this idea of symmetry here. So what you want to do is you want to draw the distribution and then put 0.9500 in between, and then subtract this number from 1 and divide that by 2 to get the upper tail probability and the lower tail probability and the upper tail probability, right? And then this would be negative 1.96 and 1.96. Okay, that is week 2.